Okay, so today's lesson is inductive reasoning. We have the definition of inductive reasoning. It's making conclusions based upon observations and patterns. Oftentimes, most type of reasoning that you're going to do in any situation or many situations is inductive. We naturally pick up on patterns and try to make conclusions from them. So the first one that we have is visual patterns. All right. A couple of things that we need to discuss is what's a term. A term is a pattern that refers to the value of an element in the pattern. Notation-wise, n refers to the term's place. A sub n refers to the term of n place. Right. So, example, we've got a pattern 5, 10, 15, 20, 25. Right. 5 is the first place, 15 is the third place, and 25 is the fifth place. Another example, dot pattern shown below. How many dots would there be in the bottom row of the fourth figure? What would be the total number of dots in the sixth figure? So we take a look at the pattern going on. It looks like, let's see, here's the first term's got 1 dot, the second term's got 3. It looks like we added on another row of 2. And then we've got the third term. Let's be consistent. Third term, we added on another row to the previous one. So the fourth one, the bottom rows, we probably would reason to have 4 dots. Huh? And then on the sixth, we conjecture that it would have 6 dots on the bottom row. But then for sure, we would have a row of 5 on top. And above that, a row of 4, 3, 2, and 1. Right. So how many dots are in the sixth figure or the sixth term? We've got 6, 5, 4, 3, 2, and 1. We're going to add those all up. And we would end up with, let's see, 15, 21 dots. A little bit more complex of a visual pattern. Here we've got what looks to be a square with some triangles around it on the first term. On the second one, we've got another square with triangles around it, and it seems to be adding on as we continue. Now the first question is asking, what's the 0th term? Right? So what precedes number 1? Right? So because the pattern looks like it's adding on a square and two triangles each time. So if I were to take that away and go backwards instead to get the 0th term, seems like I would get something that looks like this, like 2 triangles next to each other. How can we find the number of triangles if we know the figure number? Okay, so if we take a look, how do we know the figure? If we know the figure number, we'll know how many squares there are, right? Because figure 1 has 1 square. And we can figure out the number of squares by multiplying. So the number of squares is, let's see, or we can figure out the number of triangles using the number of squares. Sorry. So number of triangles equals twice the number of squares, so 2 times the number of squares plus the 2n squares, right? Or our 0th term if you think about that. So because the figure number equals the number of squares, the number of triangles equals 2 times the figure number, or the term number, plus 2. So how many triangles would be in the 10th figure? Well, I'm going to take this formula that we have, the number of triangles equals 2 times 10 plus 2, which gets me 20 plus 2 is 22. So we have 22 triangles in the 10th figure. If one of these figures contains 24 triangles, I'm sorry, 34 triangles, how many squares would be in that figure? So we can use the same formula as we did before here, because we know that the figure number equals the number of squares. So 34 equals 2 times the number of squares plus 2. So subtract 2 from both sides, I get 32 equals 2 times the number of squares. And I will get 16 equals the number of squares. Oops. All right, so number patterns, a couple of guidelines when we deal with number patterns, so anything that's not visual. Couple things that you should do is always find the 0th term. If the pattern has fractions, separate the numerator and denominator into two different patterns. Remember that the numerator is on top of the fraction and the denominator is on the bottom. If the pattern is repeatedly adding a number, then we're going to multiply that number by n. Right? That's going to be the rule then. If the pattern is repeatedly multiplying, then the number is the base with a power of n. The guidelines for 3 and 4 will be a little easier to see once we go over a couple examples here. Alright, so we've got our first pattern, 2, 4, 6, 8, and 10. It says describe the pattern and try to find an equation that works for every term in the pattern. So see if you can figure it out here. Give it a pause. Alright, taking a look at this one. I think most of us would understand that this is increasing or adding to each time. So because this is repeatedly adding to, the rule becomes 2n. But there's still a little bit that we have to figure out. We should always figure out what is the 0th term. All right, so we got the general rule, but now we've got to figure out its starting point. So I've got to subtract 2 from 2, and the 0th term equals 0 in this case. So I'm going to combine these two into a rule using proper notation. So use a sub n equals 2n, and we don't have to write the plus 0. Right? But if it was something besides 0, we should add that in. So what is the 19th term in the pattern? So what we're trying to figure out is a sub 19 and that's going to be 2 times 19, which gets us 38. Let's go on to the next example. Give it a pause right here and see if you can do it yourself. All right. So in this one, again, we're adding 2 each time. So when it's asking for the nth term, it's basically asking for what's the rule. All right. So if we're adding 2 each time, we know the base is going to be 2n. But we still got to think about what is that 0th term. So I've got to take 1, and I've got to subtract 2. I've got to go backwards to get that 0th term, which gets me a -1. So when I combine this all into a rule, I've got 2n, and I'm going to add a -1, or, in other words, subtract 1. So what's the 34th term in this pattern? We're looking for a sub 34. 2 times 34, subtract 1. I get 68 subtract 1, which gets me 67. That's the 34th term. Here's our next example. Go ahead and take a look at it. See if you can figure out what's going on. Look carefully, we're multiplying 5 each time. So if we're multiplying by 5, again, you take that, the 5 becomes our base, and we have it to the nth power. But now we have to figure out what's the 0th term. So we got to go backwards one step. What is 5 divided by 5? Which is 1. So 5 divided by 5, which gets us 1. So the rule then is a sub n equals 1 times 5 to the nth power. Now, do I have to have, in this case, have the 1 there? No, I actually don't. So I can actually get rid of that and just have it 5 to the n. What's the 15th term? So a sub 15 equals 5 to the 15th power. Gets me something really big. We got 30 billion 578,125. Take a look at this one, give it a pause so you can figure it out. All right, this one again is multiplying by 2 each time. So we know that it's going to be a 2 to the n power. We've got to figure out what is the 0th term next. So I've got to take 3 and divide it by 2. Since that doesn't work out nicely, I get a decimal, I'm just going to leave it as a fraction. Okay? So the rule then becomes 3 halves times 2 to the nth power. So what's the 10th term in the pattern? 3 over 2 times 2 to the 10th power. I'll probably end up using the calculator on this one. That's okay. You'll get 1,536.